functions of two variables. And it's important to remember that our general description of the functions are the same. That is, it's an input-output machine. If you give one input, it can only give you one output. But we're allowed to put in more complicated stuff now. We'll start with functions of two variables, which means you're allowed to plug in a point inside two-dimensional space. The variables are thought of as being independent variables. So we usually typically call that the x variable, and y variables are independent variables. You can choose a value from one independent of the other. The numbers that you're allowed to plug in for x and y are going to be called the domain, and that's usually a subset of the xy plane. So some sort of blob like this. When we say function of two variables, we really mean the output is being just one value. So we represent that as a dependent variable. In this case, we typically call that the z variable. The possible values that you can get out of your function is called the range. And it'll take values along a number line. Generally speaking, we can define functions as tables. So you would have, if you're defining as tables, you would have two columns of values you're allowed to choose independently. One column is for the x values, the other column is for the y values, and the third column would be your output values. We can also describe functions with graphs, but again, in this case, it'll be more complicated, where the domain of your graph will represent in a plane, if the xy plane specifically, and your output is going to be some sort of value along the z-axis. But in this first section, we're going to define our functions with equations. And those equations look like something like this, where the top example we have in the book is an equation of two variables, defines a plane. G as a function of x and y would be an equation that is more complicated, but if I recognize it as the upper hemisphere of a sphere with radius, it looks like 3. The first skill you want to get down is using the tricks that you know for finding the domain and range of a single variable function, extending those tricks to multivariable functions. When we define a function in terms of an equation, we don't necessarily explicitly say what the domain or range is, because we expect you to be able to find the domain and range. Essentially, you're not allowed to divide by 0. If you're looking for outputs that are real numbers, you can't take the square root of a negative number, that kind of thing. So for this first example, I want to take a look at finding the domain and range for this linear kind of function, function f. We'll begin with the domain, and it's actually the easiest, because if you look at this, you realize you're allowed to plug in any x you want, any real number in for x, and any real number in for y, and in both cases, you can multiply and add and subtract numbers without problems, which means there are no restrictions to what you can plug in for your x and y independently. That means your domain is going to be all of the xy plane. I can represent that as R2 notation. I can represent it in terms of set notation, which I read this as the ordered x and y are the ordered pairs, written in this way, such that x is allowed to take any real number, so anything larger than negative infinity and smaller than positive infinity, and y is also allowed to take any real number. Next, when you try to find the range, you usually use the same general strategy. A number that represents z, or that you can place z with, belongs to the range if you can find some ordered pair x and y, such that if you plug the x and y into your function, you get back the z that you're looking for. In other words, you're looking for all real numbers z, such that this particular equation has at least one solution. Now, because this is a linear equation, you can use simple algebraic tricks to solve it, and in fact there will be multiple solutions. So I can make my life a little bit easier with trying to find a solution to this equation by just saying, well, I'm going to restrict myself to all y's equal to 0. I'm going to say that in this case there's going to be enough freedom in x to be able to solve this equation even if you eliminate the y's. Using basic algebra tricks, I go ahead and solve this equation for x, and this is telling me for any choice of z, if I can plug a z into here, as long as I can find a z, for any possible choice of z, if I substitute into this equation to find the appropriate x, and any choice of y equal to 0, then the ordered pair is a solution to the above equation. In other words, substituting this ordered pair into my function will eventually simplify down to just being z. And that works for any number that z could possibly be. Or in other words, z can be any real number. Thus, the range are all real numbers. So we're going to find the domain of G as a slightly more complicated example. The nice thing about this example is it shows a little bit more generalized technique to figure out what the domain and range is. You want to look at your functions and see, are you taking the log of something? Are you taking the square root of something? Are you dividing by some sort of expression here? If you are, then you have potential of plugging in a number that you're not allowed to take the log of in this case. The general trick for something like this is to realize that you're taking the log of a combined quantity. You want to imagine there's a box of this combined quantity, and that box has a restriction. Specifically, you cannot take the log of a negative number or 0. Whatever you're plugging into your log has to be a positive number, and that means this entire box has to give you a positive number. A nice, useful trick to help you figure out what numbers you can plug in for x and y, what order pairs you can plug in for x, y that guarantee that this expression is true, this inequality is true, is to basically graph the curve that this equation defines and test points on either side of the curve. What I mean by that is I say, take this inequality and set it equal to 0. Now I have an equation that defines a curve, and I can use techniques to try to graph that curve. I have a choice. I can either plug this curve into a graphing calculator like GeoGebra or something else and just see what that curve is. Or I can use my previous curve drawing techniques, which is find some points on this particular curve that solve this equation. So set one of my variables equal to 0, solve for the other. So if I set my x equal to 0, I get two solutions, a positive 4 and negative 4 for my y coordinate, and I plot those points over here. I have the same thing from similar trick to set my y equal to 0 and solve this above equation, which gives me a solution of 2 and negative 2. Then I recognize, because I know enough about equations, that this looks a lot like the equation of a circle. Well, more accurately, it's the equation of an ellipse. So I'm pretty sure I'm just going to connect these dots within a little ellipse shape. Then I want to remember that I'm not allowed to get a 0, plug a 0 into my natural log. So the first thing I want to notice is that, well, if I plug in, say, this point 0 and negative 4 into my this expression over here, I will get a 0, which I'm not allowed to. So specifically, if I plug in a 0 and negative 4 into the equation above, I will have this blue box reduced down to 0, and I will take the natural log of 0. So what that's telling me is that I don't want to plug in ordered pairs in my xy plane that guarantee that I get a 0 within my blue box. In other words, I don't want to plug in points along the curve, that is the ellipse that I have here, because that would guarantee that I will get a 0 out of this equation, and then I wouldn't be able to evaluate my natural log. So the ellipse itself cannot be part of the domain. The question is, well, in my x ordered pairs of x and y plane, how about a point inside the ellipse, and how about a point outside of the ellipse? If I test the origin, that's a point inside the ellipse, I get a natural log of 16. 16 was what I would get out of if I test the origin inside the ellipse, I see that I get a 0 for my x, a 0 for my y, which reduces this blue box down to 16, and I can take the natural log of any positive number, including 16. So I can evaluate my function over here at the origin. Origin is part of the domain. The thing is that as long as I get a positive number, so the number greater than 0 out of this expression, it will be part of my domain because I can take the natural log of any positive number. Also, this quadratic expression over here is basically a continuous function. So if I have one point where it's positive, it will be positive everywhere away from that point up until it hits to a point that's 0. That is, up until it hits this boundary curve. the boundary curve of the ellipse that I just found by setting this equation equal to 0. Once I cross outside, though, to some point out here, like say a negative 4 for my x-coordinate and a positive 0 for my y, or a 0 for my y-coordinate, I get a negative number. So a point over here, I would get a negative number inside my log, and I don't want imaginary numbers, so I'm not allowed to get a negative number inside my log. So any point outside of the ellipse is not in the domain. Because it's a log, any point on the ellipse is not in the domain, and any point outside. Only the stuff inside the ellipse is inside the domain. If I want to mathematically describe what the domain is, it would be any ordered pair where this equation, the equation for ellipse, gives me something greater than 0. I don't really have to do a better description than that, though I probably should include a graph of what I'm talking about, so it's easier for the layperson to see. To find the range of this function, you kind of start the same way as the previous example. That is, you set up an equation that you hope to solve. You let z be general enough so that you understand what you're looking for is for any choice of z, can you find a solution, an xy ordered pair that solves the equation that you can plug back into your function to find the solution. Notice there is an outside function here that we're familiar with, which is the natural log. And it is extremely helpful to remember the domain and range of a natural log. The natural log says that as long as you're allowed to plug in any positive number less than 0 and any positive number greater than 0, the range of that natural log is going to be any real number. You can look down and see as far as you go. Well, this graph is terrible, but if you go down, you can go as far as you want, and you'll still see that this log can get there with just a small enough positive number. If you think, well, okay, it looks like this graph is topping off, I can plug in, it looks like this graph is topping off, there'll be some maximal number I can get out of the log. Well, you keep moving over and realize, no, it's going up slow, but there actually is no maximum number that you can get out of a log. Natural log can get any real number out of it. The only two caveats are, as long as you're allowed to get a number as low as you imagine, as close to 0 without going over 0 as you like, then you can get any negative number out of your natural log. So your range should be bounded below by negative infinity. Then if you look at the other side, well, as long as you can plug in any positive number inside your input of your natural log, you can get any positive output or real number in the output, so up to positive infinity. So the question is there a bound for our particular equation in terms of how big our number we're allowed to plug into our natural log can be? If you look at this graph, we realize that we're only allowed to plug numbers that are inside the ellipse. So there's some, and you must also try to remember that the closer you get to the boundary or the ellipse, the closer this box number over here is going to get to 0, but still be positive. So I can get as close to 0 as I want. So there should be no lower bound to what my z can be. But if I want to get larger and larger numbers into this blue box, I have to go closer and closer to the origin on my graph in terms of my ordered pairs. In fact, the largest number that I can get out of this ordered this box, this expression over here, is right at the origin, which happens to be 16. That means the largest number I'm allowed to plug into my natural log happens to be 16, so there'll be a largest number I can get out of my natural log, which is ln of 16. So my range happens to be all real numbers that are less than the natural log of 16.